Welcome to the deep dive. Today we're tackling, well, a really interesting puzzle. How do you get truly random numbers onto a blockchain?
Yeah, it sounds simple, maybe, but it's not.
Not at all, especially when you have this system where, every single participant has to agree on everything. Absolute consensus, getting genuine unpredictability. That's a surprisingly tough nut to crack.
That's exactly right. I mean, the whole point of a blockchain, that core need for consensus, it just makes the usual ways of getting random numbers totally unsuitable.
Why is that?
Well, think about it. If even one person, one node, could predict, or worse, manipulate a random number, it could really mess with the integrity of the whole decentralized system.
Okay, right. So consensus makes standard randomness impossible.
Yeah.
How do we actually get real randomness into this world of perfect agreement then?
That's where Chainlink VRF enters the picture.
VRF.
Verifiable Random Function. You can think of it as like a secure source for randomness. And crucially, it's provable, designed specifically for smart contracts.
Provable randomness for smart contracts.
Okay.
Exactly. Chainlink VRF has this, well, really clever solution. It uses something called the request and receive cycle.
Request and receive.
Yeah. So when a smart contract needs a random number, it doesn't just magically appear. The contract actually sends out a request to a Chainlink oracle.
All right, let's unpack that a bit. The contract requests randomness.
Uh-huh.
An oracle gets the request, and then the oracle generates the number.
It generates the random number, yes. But, and this is really important, there's a second step, a vital one.
Okay, what's that?
Along with the random number itself, the oracle creates a cryptographic proof.
A proof, like evidence.
Kinda, yeah.
Yeah.
It acts like a tamper-evident seal. It mathematically guarantees that the random number hasn't been fiddled with, and that it was generated in a way anyone can verify.
So verifiable.
That proof is the game changer. It means the smart contract doesn't just have to trust Chainlink. It can actually verify the randomness itself is legit, that trustless verification. That's like core blockchain stuff.
Okay, so the oracle generates the number and the proof. Then what?
Then the oracle sends both of those things, the number and the proof, back to the smart contract that asked for it in the first place.
And the smart contract can check the proof itself.
Yeah.
Independently.
Precisely. It can check that proof, make sure the randomness is genuine. It's like, imagine getting dice, but they come with a certificate of authenticity that anyone can look at and confirm they're not loaded.
Gotcha. That makes sense.
So to really show how this works, in practice, we thought we'd use a fun example today. Forget the super technical stuff for a second. We're going to Westeros.
Oh, okay. Game of Thrones. Now you got my attention.
Yeah.
So we're looking at a Game of Thrones themed smart contract. What does it do?
Well, this contract, its job is basically to assign a house in Westeros to a user, kind of like rolling a 20-sided die.
A D20, like in Dungeons and Dragons.
Exactly. The D20 and the contract name, VRF D20, refers to that. So
Sure.
based on the random number that Chainlink VRF generates, you might get assigned House Targaryen or Lannister, maybe Stark. You get the idea.
And the randomness comes from VRF.
Yes, and because it's verifiable randomness, it ensures the whole process is fair. You couldn't really do that reliably with older methods on chain.
Okay, I like this. So our mission for this deep dive, and yeah, we're accepting it, is to really get how Chainlink VRF works, how it makes this on-chain randomness happen, all by looking at this Game of Thrones house sorting hat contract.
Huh. Yeah, basically. Sounds like a plan, a quest, maybe?
Indeed. So let's back up just a little. Why is it so hard to just generate randomness inside the smart contract itself? You mentioned consensus earlier.
Right, we touched on it, but it's key. Every single node, every computer participating in the blockchain network has to get the exact same result for any calculation. That's consensus.
Okay, so if you try to use something simple like, I don't know, the timestamp of the last block or some other data that's already on the chain.
It wouldn't work for randomness, because everyone on the network can see that information ahead of time. It's predictable.
Not very random then.
Not at all. And if you just stored the random number on the chain itself, well, anyone could just look it up before it's used. Defeats the whole purpose for anything needing real unpredictability, whether it's our Game of Thrones houses or, more serious stuff like fair lotteries.
Makes total sense.
Yeah.
So Chainlink VRF comes in as this external verifiable source. You mentioned the request and receive cycle. Let's get into the nitty-gritty of that. How does it actually work? You said it's not like Chainlink data feeds.
Right, good distinction. Data feeds are things like price information, oracles broadcast that, and contracts can just read it. It's public.
But randomness can't be public.
Exactly. A truly random number shouldn't be known until the moment you need to use it. If it was just posted publicly like a price feed, its predictability would make it useless for, well, being random. The request and receive cycle makes sure the randomness is generated just for that specific request and it's not revealed beforehand.
Okay, walk us through the steps then. Our Game of Thrones contract needs to assign a house. What happens?
So, the cycle kicks off when the smart contract, or VRF-D20 contract, initiates a request. It basically sends a signal out to the Chainlink network saying, hey, we need a random number over here.
Got it. Request goes out. And a Chainlink oracle picks it up?
Yep, an oracle node on the Chainlink network gets selected to handle the request. That oracle then does the work, generates the random number.
And the proof. Don't forget the proof.
And the proof, right. That cryptographic proof, it mathematically links the random number back to, like, the oracle's own secret key and the specific details of the request itself.
So it's tied together securely. It's not just some number plucked out of thin air. It's connected, verifiably, to the request and the oracle. What's next?
The oracle then sends both things, the random number and that proof, back to the smart contract that asked for it.
And this is where the VR in VRF, the verifiable part, really matters.
Absolutely. Once the contract gets the number and the proof back, it uses some predefined crypto functions to check that proof.
To verify it.
Exactly, to verify it. This check confirms, okay, this number was generated by the right Chainlink oracle, and nope, it hasn't been messed with along the way. If the proof checks out, the contract can confidently use that random number. Assign the Game of Thrones house.
Sounds incredibly secure.
Mm.
But these requests, they don't just happen for free, right? How does the payment work?
Good question. No, they're not free. Chainlink VRF requests are paid for using prepaid subscription accounts.
Subscription accounts, like a prepaid phone plan.
Sort of, yeah. You set up an account, load it up with credits, specifically LINK tokens, and those credits get used whenever your contract makes a request for randomness.
So the person who made our Game of Thrones contract, they need to set up one of these accounts.
Precisely. They'd use the Chainlink Subscription Manager tool. That's where you create the account, fund it, manage it. It makes it pretty straightforward to handle the costs for your application's randomness needs in one place.
Okay, so contract asks for randomness, pays via subscription. Let's dive back into our VRF D20 Game of Thrones contract.
Right.
What's its main job again?
Its main purpose is just to simulate rolling that 20-sided die, and based on the result, assign a Game of Thrones house to a user's address. It's a simple but clear way to show how you can use this secure on-chain randomness.
And what are the key functions inside the contract that make this happen?
Okay, there are a few main ones. First up is rollDice. That's the function that actually kicks off the request to Chainlink VRF.
Who calls that function?
Well, in this specific example, it's set up so only the owner of the contract can call it. There's a modifier, only owner, that restricts it.
And the owner's usually the one who deployed the contract?
Typically, yes. It allows for some control. The rollDice function also checks first if the address trying to roll has already got a house. You can only get one roll. And when it successfully starts the process, it emits an event, a dice rolled event, which basically logs the action on the blockchain.
Okay, owner calls rollDice, request goes out. Chainlink Oracle does its thing. Then what?
Then the Chainlink Oracle calls back to the smart contract. Specifically, it calls a function named fulfillRandomWords.
FulfillRandomWords. That sounds important.
It is. It's actually part of the base contract, VRF Consumer Base V2, that our VRF D20 contract inherits from. It's designed to receive the answer from the oracle. The oracle sends back the random number it generated, or numbers, plural, if you asked for more than one. In our case, just one.
And how does that number, which could be huge, turn into a Game of Thrones house, like number 1 to 20?
Right. Inside fulfillRandomWords, the contract takes that random number it received and transforms it. Usually this involves the modulo operator.
Modulo, like finding the remainder.
Exactly. You take the big random number, do a modulo 20 operation, which gives you a result from 0 to 19. Then you just add 1. Boom, you have a number between 1 and 20.
Clever.
Once it has that 1 to 20 number, the contract updates its internal records. It stores that house number, linking it to the address that started the roll. And then it emits another event, dice landed, to record the result on-chain.
Okay, that maps the randomness. Now, what if I, or someone else, wants to see which house they got assigned?
For that, there's the house function. Anyone can call this one. You just give it an Ethereum address, and it tells you which GOT house is assigned to that address. It also has some checks, to make sure the dice was actually rolled for that address, and the result isn't still, pending.
Makes sense. And how does it know, say, that 1 means Targaryen and 3 means Stark?
Good question. It uses another function, a private one called getHouseName. This function basically just holds a list or an array mapping numbers to names. So 1 is Targaryen, 2 is Lannister, 3 is Stark, and so on, all the way to 20.
So it looks up the name using the number.
Exactly. When the house function needs the name, it takes the number result, maybe adjusts it slightly for array indexing. Arrays usually start at 0, and uses that to find the right name in the list.
Brilliant. Okay, functions make sense. What about the data inside the contract? The variables, what are the important ones?
Right, several key variables. There's subscriptioned, that's just the ID number of that prepaid subscription account we talked about, the one used for paying Chainlink. Then Sonar, which just stores the address of the person who deployed the contract. Simple enough. Then you have Coordinator and VRF Coordinator. These hold the actual blockchain address for the main Chainlink VRF Coordinator contract on the network we're using.
Which network is this example on?
This example uses the Sepolia testnet, so that address, 0x8103, ending in 0.4625, that's the specific address for the VRF coordinator on Sepolia. It's like the main switchboard the contract talks to for VRF services.
Got it. Coordinator address. What else?
Another really important one is ski hash. It's got this long hexadecimal value, 0x474E. You can think of the key hash as specifying like type of Oracle service you want. Different key hashes might relate to different security levels or speeds, and they also signal the maximum gas price you're willing to pay for the Oracle's response transaction.
So it's like choosing your service level.
Kind of, yeah. Then there's callback gas limit. In the example, it's set to 40,000. This tells the Oracle the maximum amount of gas, computational effort it's allowed to use when it calls back to our contract's fulfillRandomWords function. Setting this high enough is critical, otherwise the callback might fail if it runs out of gas doing its work.
Need enough fuel for the return trip.
Exactly. Then request confirmation set to 3. This tells the Chainlink node how many blocks to wait after seeing the request before it actually generates and sends back the randomness. Waiting for a few confirmations adds security against things like block reorgs.
Free blocks, okay.
And finally, numwords. It's set to 1 here. This just says we only need 1 random number per request. If your game or application needed, say, 5 different random numbers, you could set numwords to 5 and get them all in one go, which can sometimes save on gas compared to making 5 separate requests.
Wow, okay, lots of specific configuration there. How does the contract actually keep track of who rolled the dice and what result they got? You mentioned linking the address and the result.
Right. It uses 2 main data structures for that. They're called mappings in Solidity. Think of them like dictionaries or key value stores.
Okay.
The first one, Srollers, maps a unique requested, which gets generated for each randomness request, to the Ethereum address that made that request. This way, when the answer comes back with that requested, the contract knows which user it belongs to.
Links the request ID to the user address. Got it.
The second mapping, results, maps a user's Ethereum address directly to the result of their dice roll. Initially, when the roll starts, it might store a placeholder value, like roll in progress. The contract defines this as 42, just an arbitrary number meaning not done yet. Then, once fulfillRandomWords runs successfully, it updates this mapping, storing the actual house number 1 to 20 for that user's address.
So Srollers tracks who asked, results tracks what they got. Makes sense. You also mentioned importing libraries from Chainlink, like VRF Consumer Base v2. Why do that?
Yeah. Importing VRF Consumer Base v2 and also VRF Coordinator v2 interface just makes life much easier for the developer.
How so?
Well, VRF Consumer Base v2 gives you a lot of the foundational structure and functions you need already built. Like, it includes the basic logic for making requests, and critically, it defines that fulfillRandomWords function that the Oracle needs to call back. You just have to fill in the specifics for your contract.
This is like a template.
Kind of, yeah, a base template. And VRF Coordinator v2 interface provides a clear, standardized way for your contract to talk to the main VRF Coordinator contract on the network. It defines all the functions you can call on the coordinator. Using these imports just saves time and reduces the chance of making mistakes when interacting with the whole Chainlink VRF system.
Like using pre-made building blocks instead of starting from scratch every time.
Exactly. Much more efficient and less error-prone.
Okay, so if someone listening wanted to actually try this out, deploy this Game of Thrones contract themselves, what are the basic steps? The docs mentioned Sepolia testnet, maybe using Remix.
Yeah, that's a typical way to experiment. First, you'd compile the Solidity code for the VRFD20 contract. You can use an online IDE like Remix for that.
Okay, compile the code.
Then, when you go to deploy it onto the Sepolia testnet, you'll need to provide that subscription, the ID for your VRF subscription account, as an argument during deployment.
Right, you need the subscription ID ready.
Yep. And once the contract is actually deployed on Sepolia, it has its own address. But it can't use your subscription yet. You have to go to the Chainlink Subscription Manager interface, find your subscription, and explicitly add your newly deployed contract's address as an approved consumer.
Authorize the contract to use the funds.
Exactly. And of course, you need to make sure that subscription account actually has enough LANK tokens in it to pay for the VRF requests.
Gotta fund it.
Fund it, approve the contract, then what?
Then you're ready to test. You can call the rollDice function, probably from Remix again, providing an Ethereum address you want to assign a house to. Then you wait a little bit.
Depends on network conditions and those request confirmations, but usually not too long on a testnet. Maybe 30 seconds, a minute. Enough time for the request to get confirmed, the Oracle to process it, and the callback transaction to get mined.
Okay, wait a bit.
And then you can call the house function, giving it the same Ethereum address you used in rollDice, and it should return the name of the Game of Thrones house that was randomly assigned by Chainlink VRF.
Cool, so it's a multi-step process, but it shows the whole cycle. Deploy, fund, approve, request, wait, receive, check, result.
Exactly. It demonstrates the whole life cycle. And, while this Game of Thrones example is fun and pretty simple,
Yeah.
the underlying principles, the secure, verifiable on-chain randomness from Chainlink VRF, it has really significant implications for all sorts of blockchain applications, much bigger than just assigning fantasy houses.
Absolutely. So just to quickly recap then, we talked about why getting real random numbers on a blockchain is hard, that whole consensus thing.
Right.
Then we saw how Chainlink VRF offers this really solid, trustworthy solution with its request and receive cycle. The smart contract asks, the Oracle generates the number, and that crucial cryptographic proof sends it back, and the contract verifies it.
Yep, verification is key.
And our Game of Thrones contract, the VRFD20, was a great way to see that in action, how it requests, gets, and then uses that provably random number to do something concrete, like assigning a house based on a D20 roll.
And really what's exciting is thinking about the potential this unlocks. I mean, far beyond just games or lotteries, those are important too.
Like what?
Well, imagine truly unbiased ways to select participants in DAOs, decentralized autonomous organizations, or creating NFTs, non-fungible tokens that are genuinely dynamic and unpredictable in their traits based on this randomness. There are just so many possibilities. This tech could really fuel a whole new generation of innovative blockchain apps.
That is a really interesting thought. That makes you wonder, doesn't it? What other kinds of maybe unforeseen innovative uses for secure on-chain randomness might we see as this technology gets, more widely adopted and built upon? Really sparks the imagination about what comes next.
It does.
And for anyone listening who wants to go deeper, the Chainlink documentation is fantastic. It covers tons of use cases like over 35 different ones for blockchain RNG, stuff on dynamic NFTs, details about VRF v2 on mainnet.
Yeah, the docs are really comprehensive.
Plus, there's a What's Next section guiding you on how to actually get a random number, manage subscriptions programmatically, security best practices, supported networks. Plenty to explore.
Yeah.
Definitely worth digging into if this has piqued your interest.
Indeed. It's a big landscape, but understanding these core mechanics of Chainlink VRF, that's a really crucial step if you want to build or understand the next wave of decentralized applications.